heterogeneous nucleation starts. So, driving force, or maybe here the driving force may be the different in case of heterogeneous welding process, but the in case of heterogeneous nucleation process, any kind of inclusion presence in the liquid metal or any interface or any surface, they actually start, they actually initiate the, at this point there is a initiation of the nucleation happens in case of the heterogeneous nucleation process. So, if we simply represent that what is the amount of the optimum amount of the energy required in case of the heterogeneous nucleation process, that is the amount of the energy, optimum energy required for the homogeneous nucleation process into some factor, that S is the as a function of theta. So, that factor S actually intuitively depend on the size shape of the nucleus, because when the heterogeneous nucleation happens based on the nucleation theory over the interface, the surface tension between this interface or surface and the liquid metal can be different as compared to the only the surface tension of the completely solid metal when it is the solid metal exists within the liquid molten pool. That happens in case of the homogeneous nucleation process. So, that is why depending upon that S theta is the shape of the shape and of the nucleus, and of course, this as a function of the shape of the nucleus, and this S theta can vary from 0 to 1 in between 0 to 1. So, if we typically plot the total free energy change in case of homogeneous nucleation process and in case of heterogeneous nucleation process, we can find out the difference here. Here we can see that amount of the heterogeneous nucleation process, the barrier to start the nucleation process is less in case of the heterogeneous nucleation as compared to the homogeneous nucleation process. So, this amount, total amount is the amount to critical amount of the energy required for the to start the homogeneous nucleation process, and this is only the small amount that start the nucleation process in case of heterogeneous nucleation. But critical size of the nucleus both the cases is the same, because that the critical size of the nucleus is intuitively depend on the volume free energy and the surface specific surface energy of the material, of the particle basically. So, that is why it is the critical size of the nucleus is independent of the shape of the nucleus. Now, we will try to look into that solidification in case of the binary alloy system. So, here the liquid of the uniform composition rarely uniform after the solidification, because we assume the liquid of the uniform composition, but after the solidification it may not be the uniform, and solute atoms in the liquid, the redistribution solute atoms in the liquid, that also happens, the redistribution of the solute atoms during the solidification process. So, redistribution of the solute atom in the solidification process in specific to binary alloy, that actually depends on the thermodynamics, that means phase diagram, and kinetics. Kinetics means the diffusion, undercooling, and in any material flow. Of course, undercooling, these are the kinetics, and that fluid flow, all these are the influencing factor for redistribution of the solute atoms in case of the binary alloy system. Now, if we look into one typical phase diagram, binary phase diagram, here if you see that there is a liquidous line, and we representing the liquidous and solidus line as a straight line. So, and if we pick up any initial composition of the solutes, x axis represents the solute concentration and y axis represents the temperature. So, at any solute concentration, so if we assume the initial solute concentration at this point C0. So, at this point if you draw one vertical line, so this point corresponds to that liquidus temperature, and this point corresponds to that solidus temperature. Similarly, if we consider the concentration are different, the liquidus and the solidus temperature can be different depending upon the liquidus line and the solidus line, and for a with the different composition. So, with this composition, the liquidus line here equal to TL, and solidus temperature is basically it represents by the TS, and at any temperature in between the solidus and liquidus, because between the solidus and liquidus temperature there may be the solid content and the liquid content. So, at any temperature in the case of the initial concentration, initial composition of the binary alloy is the C0. So, in between temperature, so this represents the liquid content. So, that means with respect to the any temperature line, if we draw one horizontal line, so that actually cross the liquidus temperature and solidus temperature. So, that liquidus temperature, this point correspond to that, this actually represents the liquid content, and which that at that point corresponds to the solidus line, that actually represents the solid content. So, that means we can say that although initial composition of the metal is concentration is C0, so in between the liquid and the solidus temperature, that consists of the liquid content and solid content. So, that can be this amount, the solid content and liquid content can be evaluated simply using the simply in a proportionate way. We can usually find out what is the amount of the liquid composition, what is the amount of the solid concentration within on a specific temperature. So, here also you can see that C0, and that when this C0 composition correspond to the liquidus line, when it cross the liquidus line, liquidus, it cross the liquidus line, and that corresponding point, if you draw one temperature line, the basically liquidus temperature. So, which point it cross that solidus line, this composition is corresponds to the K into C0. So, definitely here K should be the less than 1, that means less than 1 means their liquid content for this case in this case is basically less than C0. Now, if we further discuss on the phase diagram, so we assume the initial composition C0 and the solidification starts when the liquid cools down to the TL cools to the TL. So, solidification starts because at this composition, and solidification when it cools to the TL, the solidification when it comes to the some superheating temperature, and when it comes at this point, the TL point, exactly the solidification starts, and gradually it solidify, it comes to the solidus line, then we can say the solidification complete. That means, in the solidus line, it is the phase is completely solid phase, but the concentration composition of the concentration is exactly at the same amount C0. It is simply following this vertical line, it starts from the solidification starts at this point, and gradually it reach this point, that completes the solidification. So, we can analyze by using the lever rule in between the solidus and liquidus temperature, we can find out the composition, that means liquid content and the solid content from this binary phase diagram. Now, what is the typical point at that? So, at any temperature T, the Cs and Cs represents the solid content and Cl represents the composition of the liquid, and basically the here the coexisting of the liquid and the solid phase here. Now, at equilibrium temperature T, the partition ratio or the equilibrium segregation coefficients between these two, that K can be represented, small k can be represented by the ratio of the Cs by Cl. It is a simply a composition of the solid composition and the liquid composition, but this composition corresponds to at equilibrium temperature T. So, equilibrium temperature changes T, this value of the K may change if the equilibrium solidification temperature changes. So, from this information phase diagram, we can further analyze this phase diagram in case of binary alloy, that solute content of the liquid continues to rise during the solidification by lowering the solidification temperature. So, solute content by lowering the solidification temperature, if we move along this by lowering the solidification temperature. So, at this point the definitely the solute content is more if solidification temperature is less. Second point, as the solid grows from the liquid, its solute content also continues to rise. Definitely as the solid grows from the liquid, so when it starts from the liquid phase and continuously grow towards the solid phase, the concentration of the solid phase actually increases. If K less than 1, then Cs and Cl both increases as temperature T of the solid liquid interface drops during the solidification. So, when the solidification temperature actually drops, both the Cs and corresponding Cl liquid content and the solid content actually both are increases if there is a decrement of the temperature T. The slope of the liquidous line ML is less than the 0 when K is less than 1 and vice versa. The slope, definitely here we can see this diagram, the slope is basically less than 0, that slope is basically negative in this case, and K, when K is less than 1, definitely when K is less than 1, the slope is basically negative, and of course vice versa also correct. If the liquidous line is straight, then temperature T on liquidous line can be expressed as this way. So, that if you see the if we can see that the liquidous line is straight, the any temperature T on the liquidous line can be expressed as this. So, if you see here the liquidous line is basically straight. So, at any point the temperature is T can be that melting point temperature minus that difference between the Tm and T, between that temperature. So, Tm minus T. So, that Tm minus T, the increment can be represented by the slope ML, and the slope at corresponds to the Cl. So, m into Cl, and this slope is negative. So, Tm can be represented by the T at any point can be represented by the Tm negative slope and the amount of the liquid content on that specific point. So, at this specific point, what is the slope? This actually represents that Tm. This actually represents this also mathematically says that this is also equal to that slope into that content Cl. So, this amount. So, which is equivalent to that this amount. So, that way that if liquidous line is straight, not the curve here, then a temperature T on the liquidous line can be expressed like this. So, with this understanding of the binary phase diagram during the solidification process,